All right. All right, so we're gonna go through two sample t-test. And I'm gonna show you how you can find the degrees of freedom on the calculator. There's a really nasty formula that you use to find degrees of freedom with the two sample lines, and I don't want you guys to worry about it. I don't even wanna do it. So if I don't wanna do it, I know you guys aren't gonna wanna do it. So let's see, it says, there's two competing headache remedies claim to give fast-acting relief. An experiment was performed to compare the mean length of time required for bodily absorption of brand A and brand B. It says there are 12 people that were randomly selected and given an oral dosage of brand A, and then another 12 were given brand B. The length of time of minutes for the drug to reach a specified level in the bloodstream was recorded. So the means and standard deviations of the samples are below. So these are from the sample, not the population. All right, so that means we've got to use t-test or student t-distribution because we don't know what the population standard deviation is. So, let's go to see what kind of test we're gonna do here. It says past experience with the drug composition of the two remedies permits researchers to assume that both distributions are approximately normal. We're gonna use a 5% level of significance to test the claim that there is no difference. See how I underlined it here? That's one of the key words we need to look out for. We're checking to see if there's any difference between the brands in the meantime. All right, so we're testing the means between these two. So because we are setting this up with a two sample, when you write your hypothesis for your null hypothesis, it's always going to be when you're dealing with means and you're doing two samples, it's going to be mu1 is equal to mu2. We're making the assumption when we start with that the means are the same. All the time, we're just making that assumption that the means are the same. And then when we come up with the alternative hypothesis, that's when we're going to use the less than, greater than, or not equal to, depending on what the challenge statement is, okay? And because this challenge statement is saying that there's no difference, we're going to set up our alternative hypothesis as mu1 is not equal to mu2. And then we're doing this at an alpha level of 0.05. Okay, is everybody good so far? So this is going to be the way it's set up all the time for two sample means, okay? This is just going to change depending on what the challenge statement is. Now, sometimes it might even be written, but it means the same thing. Let me get my pen. It could also be written like this, but it means exactly the same thing. It could also be mu1 minus mu2 is equal to 0. It's the same thing as this. If they're the same and I subtract them, they get 0. It means the same, okay? All right, now, because we know we have two samples that we're dealing with here, and we were not given the population standard deviation, we're going to use two sample t-test. So I'm going to go to stat over test, and I'm going to choose on mine it's option number 4, two sample t-test. And we're not given the data here, we're just given the information in the problem. So we're going to use the stats option. And then we're going to enter in all this value here, just like before. Remember, the X bar means the sample mean. SX is the sample standard deviation. Now, there's a lot of values here because we're dealing with two samples. So I'm just as guilty as doing this. So I'm like trying to give you a heads up. When you're putting in the data, just be really careful and make sure you're putting it in the right spot. Because I'm just as guilty as accidentally putting it in the wrong spot because there's so much data here. Okay, so when it asks for X bar 1, that's asking for the sample mean from the first sample. So that's this here. I'm gonna put in 21.8. Oops. I'm gonna put in 21.8. The standard deviation from the sample, and it's specifically the first sample because it has that one there, that's 8.7. And then the sample size of the first sample is 12. And then X2, that's the sample mean from the second sample, so that's gonna be 18.9. And then SX, that's the sample standard deviation from the second sample, so that's 7.5. And then the size of the second sample is 12. And since it's asking for us to check to see if there's any difference at all, we're doing two-tailed, okay? So I'm gonna choose the not equal sign here for two-tailed test. And as usual, we're always gonna use no for pooled in this class. Then I'm gonna hit calculate. Okay, and just like before, it's gonna give us the very first line, test statistic, the p-value, and then the third one down will give us the degrees of freedom. Instead of us having to calculate it with that nasty formula, just use this here for your degrees of freedom. So when you get this up, when you're making a note or you're plugging it into your XYZ boxes, I would on scratch paper off to the side, write what your degree of freedom is, because you're gonna need it for your sample or your critical value. Okay, so we've got that our test statistic is rounding to 4 places 0.8746. Our p-value is 0.3915, and then I jotted down the degrees of freedom. Don't round the degrees of freedom, keep digits, okay? Although I probably should write all of them down too. Let's see, there should be 55015. Don't round your digits for your degrees of freedom because that will throw your answer off. Wait till after you put it in on the calculator to do that, okay? Everybody okay so far? It's pretty much the same thing over and over again. You're just entering different information and depending on what test you're using. Okay, now for the rejection regions, same concept. We're gonna find our critical value. We're gonna do inverse T because we're doing student T distribution. So, and then we're just gonna use the degrees of freedom that it gives us here from the calculator, so we don't have to use that nasty formula. When you put that in on your calculator, you're gonna get negative 2.08. Now, our alpha level is 0.05 because this is two-tailed. Remember, when it's two-tailed, you have to split that 0.05 into two, which is why I put in for the area 0.025. If it wasn't two-tailed, I could put in that whole alpha level for our area, okay? Okay, so when you put that in on your T inverse, okay, we get negative 2.08. And when I did this, I was just doing it on paper, so I wasn't as careful about rounding. But remember, when you're doing this on XYZ, make sure you pay attention to the rounding directions, okay? And then once we get our critical value set up, so because it's two-tailed, I'm looking at both sides. So I have negative 2.08 on this side for this critical value, and on this side is 2.08. And then I go back and I look at my test statistic. My test statistic was 0.8746. So I'm going to look to see where that falls here. 0.8746 is going to fall between 0 and 2.08. It's going to fall in here somewhere, which means it's not in the rejection region, which means we're going to say do not reject the HO. Everybody okay with that so far? Okay. Then for the p-value, we got to check to see if the p-value is greater than or less than our alpha level. In this case, it's greater than, and when the p-value is greater than alpha, we say do not reject, HO. And these should always match up, step 3 and 4. So our final conclusion would be at the 0.05 level of significance, there is not enough evidence to support the claim that mu1 is not equal to mu2. Now, because some of you guys don't have inverse T on the calculator to do this, if you try to use the tables and you've got a degrees of freedom that's got a lot of digits like this, it's not going to give you the correct value that XYZ is expecting. I would be okay, like if you did it on paper to round it, because we're just doing on paper. This is all estimates anyways. However, the XYZ program is going to expect, because it's a computer specific values. So I really suggest that you use that calculator, that online calculator link that I sent out to you guys, so that you can put in the exact number of degrees of freedom without having to round it. Does everybody know what I'm talking about when I sent out that announcement with the link for the calculator? Okay. Do you guys want to do another one of these, or do you think you've got it? You want to do another 2 sample, or do you want to try like a Z or a P, or do you want to just be done with, and this is our example? How do you guys feel?
Can we see a Z?
Yeah, let's do a Z. All right, here's a Z. This is, I believe this is the example I use in the lesson for 10.2. Okay, it says, a teacher wishes to compare the effectiveness of 2 teaching methods for her students, and students are randomly divided into 2 groups. The first group is taught by method 1, the second group by method 2. At the end of the course, a comprehensive exam is given to all students. The first group, and it goes on to list all the information, the sample size and the sample mean and everything. And then it says the teacher claims that the second method will increase the mean score on the comprehensive exam. So we're going to say, because this is 2 sample and we're dealing with means, we're always going to start with mu1 is equal to mu2. That's a given. We're just going to make the assumption that they're the same. And then the alternative, in this case, she's saying that the method 2 is going to make the mean from that group bigger. So that means when we state this, we're going to say mean 1 is less than mean 2, because mean 2 should be bigger, according to this, the challenge statement. Is everybody okay with the way I set that up? Okay, now, as I read through here, you'll notice that it gives the population standard deviation. And this one's easy to identify because it actually gives it to you with the symbol sigma. So sigma 1 is and sigma 2 is, so that's kind of like a gimme, it's screaming at you. Sometimes it says in words, you know, the historical population standard deviation is, or it might say the standard deviation for all blah, blah, blah. So it might tell it to you in words, so you have to really read it carefully. Now, because we're given the standard deviations for the population, that's how we know we're going to use z-test. And because it's 2 sample, we're going to use 2 sample z-test. So I'm going to go to the calculator. I'm going to go over to test, and I'm going to choose, on mine it's option 3, 2 sample z-test. So far, so good, Robert?
Yep.
Okay. Now, the previous example we did, it was nice because it lined everything up for us. It said, this is S1, this is S2, this is X bar 1. It kind of had it spelled out for us. This one, we have to read through the problem carefully and get the information. So when we look at this, the sample size of the first sample is 49 students. I'm gonna go down and put for N1 49. Now the sample mean for the first sample is 74.8, so I'm gonna put that here. The second group has 50 students, so that's gonna be my N2. And it had a mean score of 81.3. So that's gonna be my sample mean for the second sample. And then here's my population standard deviations. So that's what's gonna go here, 14 and 15. I just scroll down, make sure I got everything. Okay, now this says we're checking that mu1 is less than mu2, or another way that you can say that is mu2 is greater than mu1. We want to make sure that since this is pointing to the left, this little pointy symbol is going to the left, that's the one I want to choose here. That's the left-tailed test, okay? So it's always going to be mu1 and then fill in the blank, less than or greater than, okay? Or not equal to. So this isn't two-tailed, so I don't have to split the area between the two tails. But just keep that in mind that you only have to do that for two-tailed. Then when I hit calculate, it's going to give me my test statistic and my p-value. Now, when we're doing Z, we don't have to worry about degrees of freedom. We only have to worry about degrees of freedom when we're doing T's, okay? But if we were doing T's here, this is where I would probably write it down, okay? Because I would get it right off the screen here. All right, so here's my test statistic, here's my p-value. Now I gotta find my rejection region. So because I'm using Z's here, I'm gonna use inverse norm. I'm gonna put in my area to the left is 0.05. That's the area of my wing. And then I'm gonna put in 0.1 and I'm gonna get my critical value. And remember, I'm showing you this in the video, like I already have it handwritten out. But when you go do this on XYZ, make sure you're following the rounding directions, okay? Now, because this is left-tailed, when I set up my rejection region, okay, this should stay negative because I'm looking at the negatives or the left side where I have my negative values. If this was a right-tailed test, then I would draw the graph and shade my area on this side, which means it would be a positive 1.645. So you want to make sure you're looking at the correct side of the graph. So make sure you're picking your critical value so that it's positive or negative, depending on if you're looking to the left or to the right. Now, when I look at my test statistic, that test statistic is further passed to the left of negative 1.645, which means it falls in that red rejection region, okay? So that means we're gonna say reject HO. So far, so good, Robert? Do you have any questions yet? Okay. Because it falls in that rejection region, we say reject the null. Then we check our p-value. Our p-value we got was 0.0129. And that's less than our alpha level, which was 0.05. And whenever it's less than, we say reject. So we know we're on the right track because they both came out the same. They should. And then we write our conclusion. At the 0.05 level of significance, there is enough evidence to support the claim that the mean score of the second method is higher. Did that help, Robert? Yep. Do you want to do a P also, or do you want to be done? Anybody want to do an example of a P? Okay, then do you guys just want to work now, or do you have specific homework questions you want to go over? Brandon's thinking hard on that one.
Just work.
Okay, all right, I'll leave you alone then, and then just let me know if you have questions.